It's splitting the paper.
1.6. Look at the gate up there. It's actually come down. See it? You can see it from right here. Yeah.
Oh! Oh!
The Colorado Department of Transportation has been involved in research on geosynthetically reinforced earth structures for many years. This research is now paying dividends in reduced costs for retaining walls and in reduced environmental damage during construction. Much of this research has been performed cooperatively with Oregon State University and the University of Colorado at Denver. This research has incorporated work performed by many of the outstanding researchers in the geosynthetic arena. The most recent CDOT research project involved full-scale wall testing at the University of Colorado at Denver.
Here's the loading facility that allows us to perform full-scale tests for geosynthetic reinforced retaining walls. The facility is 13 feet high, and it can be telescoped between 4 to 8 feet. The sidewall of the loading facility is made of 1-inch thick plexiglass, and is lubricated by using a latex membrane and silicone grease, a technique that I borrowed from Japanese. You can see the deformed facade of the wall, and this is the last full-scale test that we performed and used the cohesive backfill. The wall is very extensively instrumented with load cells, potentiometers, paper targets, sidewall grease systems, strain gauges, and Macklins.
The research project consisted of instrumenting 2 test walls and loading each to failure. As part of this research, a rigid steel frame was built at the Department of Transportation, and once built, the frame was disassembled, moved to the university where it was reassembled and painted. A geotextile reinforced sand wall was tested first. To achieve a uniform sand density throughout the wall, the sand was rained from a predetermined height. The geotextile reinforced clay wall was tested next. Sample preparation was significantly more tedious. The clay obtained from a nearby highway project was sieved and transported to the university. Water was added to the clay to maintain a uniform moisture content. The clay was placed within the wall to a predetermined lift height and compacted by a vibrating hand-operated compactor.
For both walls, the instrumentation consisted of strain gauges, load cells, potentiometers, paper targets, a Hall-effect generator probe, which locates the distance between magnets which were installed on the geotextile, and photographic records of the progressively deforming sidewall grid pattern.
Airbags were placed on top of the wall and inflated. The airbags would react against the top of the load frame as they expanded, thereby loading the wall. The airbag shown here is being proof tested.
You're taking air in. Air's going in there.
Air is coming there.
Right? 15?
15.
Okay, we'll go to 15.
But 20 is zero.
Stand clear.
Clear. No, we need to get about 30 people, each one responsible for one window. Yeah,
I don't think you got a lot of people.
For several months.
It goes there, it goes there, right here. This line belongs right here.
Oh, wow.
So we got about a 5-inch movement on this.
Wow. And then you can see it going back as you get a
Yeah. In fact, it is a 5-inch movement.
Does it get greater as it goes up? But then it's coming back then, right?
Yeah, it's coming back. It's coming back.
Wow.
Look at that one right there, Bob. We're doing that. See there? You see the actual cutoff coming this other way, see?
The Greek gives a very good indication. Yeah. Just like on paper.
Send us all a copy. The Colorado Department of Transportation, the University of Colorado at Denver, and the Federal Highway Administration hosted an international symposium where researchers from around the world presented Class A predictions of the results of the full-scale geosystem wall tests at Denver. One interesting result was that traditional reinforcement design methods underestimated failure by a factor of at least 10. This shows that short-term safety factors of geosystem walls are very large indeed.
Now your results show very little difference in that area.
The symposium concluded with a panel discussion. The panelists were internationally recognized experts in utilization of geosynthetics as earth reinforcement.
I'd like to thank you, the audience, for being timely and good with the points that you've raised. And so,
Just another brick in the wall.
The results of this study and other research have provided the basis for establishing design standards for CDOT geosystem walls.
The Colorado study showed that geosystems can be used in almost all situations where space is constrained, and that these geosystems typically save money, save design time, and save construction effort. They are the least disruptive to build, and they conserve natural resources. These geosystems were developed by geologists and geotechnicians to resolve special problems, and they continue to be reserved for special cases by most state DOTs. And this leads to a final and personal observation. The major factor that is delaying implementation is design responsibility. Many structural and civil engineers are not comfortable with this new technology. While geosynthetically earth-reinforced slopes and walls can save DOTs hundreds of millions of dollars on an annual basis nationally, the DOTs must accept design and construction responsibility in order to realize these savings.
For more information on CDOT geosystem research or design standards, contact Bob Barrett.
Thanks for the instrumentation. Now we know what that means.
I'll fix this up for TRB. We'll have it.
Okay, we'll have a good time with
I'll
it.
tell them, heavy-duty science. We brought in the experts. Steve Barrett showed up and fixed all the instrumentation.